Let's talk about the integral test for deciding whether a series converges or diverges. In the previous video, it was shown that this series is greater than this integral, and that integral diverges. So that means that the series diverged also. The comparison to that integral was done by graphing y equals 1 over x, and then noticing that these bars here, or left sum rectangles, had areas that were equal to the sequence values: 1, 1/2, 1/3, 1/4, 1/5. And if you added those up, those areas, that would be the same as adding up the sequence terms to get the series. Well, since that sum of those rectangles areas is greater than the area under the curve, and the area under the curve was this integral and it diverged, that means that our series diverged. Another example is this one, 1 over n squared. And we think, from our analysis of integrals, we think this 1 over n squared is probably going to converge because the sequence terms are diving to 0 faster than 1 over n. And indeed, they're diving to 0 fast enough so that the sum will converge. So we have our y equals 1 over x squared curve, because we're going to try to compare it to the 1 over x squared dx integral over here. So we see that a right rectangle sum gives us 1/4 here, and 1/9 here, which is 1 over n squared, and 1/16 there, and so on. So, but that starts at n equals 2. So that's okay. We'll just burn off the first n equals 1. When you plug in 1, that's 1 over 1 squared, which is 1. And then we'll start the series from 2 and have this. So now we'll just analyze this series, which does correspond to this picture, the rectangle areas. And you can see they're clearly under the rectangle, the integral of the function from 1, because here's the integral, here's the whole entire integral under the 1 over x squared function from 1 to infinity, and you can see that that area is greater than our series area as far as this one is concerned. So what we do is we come over to here and we say this series starting at n equals 2, represented by those rectangle areas, is less than the integral from 1 to infinity of 1 over x squared dx, which converges because it's the 1 over x to the p type, where p is greater than 1, so it converges. That means that this series starting at 2 converges, but that implies that 1 plus that converges, because certainly if you just add 1 on to whatever this converges to, that's going to be the new value that it converges to. So that means that the entire original series starting at 1 converged. Also, we have notes about the p series. That's 1 over x to the p. And just like the integrals did, if the p is greater than 1, that's when the series converges for p greater than 1, and then diverges if p is less than or equal to 1. Here's another example of using the integral test to decide whether the series converges or diverges. So here's your series, and we think that these terms are going to be diving to 0 so fast because of the e to the power in the bottom, and it's even squared down there, that we're thinking that this series converges. So we're going to go for converge. But we're going to compare it to this integral right here. But first we've got to find out that integral converges, and we certainly think it does, but it's dying for us to do a substitution. So we do that, come down to here, work out just the integral part, follow these steps with the b limit, and sure enough, the whole integral converges to 1 divided by 2e. Okay, so it converges. So now we draw our picture, y equals x over e to the x squared, and we notice we're going to do a right rectangle because we're going for convergent, and so we have to start the series at 2. So we burn off one value, plug in n equals 1, you get 1 over e to the first, which is 1 over e, and so you have the series equal to this. This integral is represented by the areas of those right rectangle bars there, and that's less than this integral because the integral is the area under the entire curve. So definitely this inequality holds, and we know that converges, that integral. That means that this integral converges, this series converges starting at 2 because it's less than something that converges. And certainly if you add on 1 over e to something that converges, it still converges. So therefore the original series converges.